So this is under supplemental material on Blackboard, the one that says hypothesis testing narrative. And let me just pop that in chat for you. Oh, question in chat. Can we go over finding percentiles? Oh yeah, definitely. Yeah, anything that you want to review in the review session, yeah, we can go over anything you would like to. All right, so I posted the PDF. The PDF is in a slightly different order because it's meant to be, I kind of arrange it so it could be printed out on a front and back side of a page, but the PDF goes part 3, then part 1, then part 2, because that way I was able to kind of squeeze everything on a single page. So, okay, so I'm not going to, read it to you verbally, but I'll give you a few minutes to kind of read through this either on your own with the PDF, or I'll kind of scroll through what I think is a decent pace, and then we'll quickly talk about it. So just read through this either on your own on a PDF or on the screen here, and then we'll come back in a couple minutes. Okay, so hopefully you made it through that, and I just want to point out a couple of important ideas here. So the first important idea is that we're interested in knowing whether days off went down. Our kind of baseline was 6.3, the thing we're comparing to, and our observed result was 5.4. And so at a very basic first pass, we say, well, 5.4 is less than 6.3, so that's in the right direction. If we were interested in knowing whether days off work went down, comparing to 6.3, and we got 7.5 for our observed number, we wouldn't really be looking at any statistics at all. We just say, well, obviously getting a number above 6.3 is not evidence that that number should be below 6.3. So that's, I think, pretty clear. So we are in the right direction. So 5.4 is less than 6.3. So this seems to provide some evidence that the true mean number of days off work has gone down with the implementation of this flex time idea. We do have an issue, though. We only took a sample. Really, what I would like to say is that, say mu new less than mu old, but I don't really know mu new and mu old, right? All that I know is x bar new, and comparing that to something like maybe mu old or x bar old or something like that. So this is really what I know. And this chance skeptic, the person who's arguing, kind of arguing as like the devil's advocate in a way, says, well, I mean, x bar new, well, but that's x bar. Like, that might be a good estimate or it might be a terrible estimate of mu. We're not really sure. So the next thing that he talks about as well, we ought to look at the standard error. In other words, is this x bar new, is that a mean of a sample of size 3 or something? Well, that probably has a pretty big standard error, and maybe that would be a valid concern. Or is this a statistic from a sample of size 100 or 1,000, in which case the standard error would be much lower. In this case, it has a standard error of 0.3. So in other words, 5.4 is less than 6.3, but it's not just like a little bit less. It's a lot less. It's something like 3 standard errors below what we would expect, right? If the mean hasn't changed, if the mean is still 6.3, and you're arguing that maybe we got an x bar that was a little bit low just by sampling error, maybe we got an x bar of 5.4 and it's just on the low side because we happen to pick a few extra people with less than normal days off and a few fewer people than we might expect with higher than normal days off. So maybe that just kind of biased things a little bit to the left. Well, that becomes hard to explain when you say, okay, well, we would need a 3 sigma event, quite a rare event, for that to happen. In other words, only something like, what did he say, 1 time out of 1,000, when we would draw such a random sample, when we would compute such an x bar from sample data, only 1 time out of 1,000 would we expect to get such an x bar that's that far below, say, a mean of 6.3, that we would come to this kind of conclusion, and that we would argue with this amount of strength that the flex time actually reduced days off. So it's never impossible for this to happen by chance error or by chance through sampling error. But if it's extremely improbable, then that's where this narrative bit comes in. As the investigator says, you have a hard choice to make. You can either kind of dig in your heels and say the mean is still 6.3 and this x bar is just a fluke event. But that such an X bar would only happen 1 out of 1,000 times. And if we're going to dig in our heels, we need, as he says here, a minor miracle to explain this data. Or the other thing we can do is we can say, okay, well, maybe I instead change my worldview. Maybe I instead say, okay, kind of before running this experiment, I thought in some sense that the mean was 6.3. I run the experiment, and the experiment strongly suggests that the mean is less than 6.3, that the introduction of the flex time has actually decreased the number of days off. So what's kind of one issue with this would seem to prove or provide evidence that flex time reduces absenteeism. We actually can't quite make that conclusion. We implemented flex time, and it does seem that we provided evidence, very important here. We haven't proved mathematically or anything like that, but we provided evidence in favor of absenteeism going down. But we would have to do more work to argue that it was actually flex time that drove absenteeism down. Maybe, maybe last year there was, maybe the flu was worse than usual, and this year it wasn't as bad. So maybe that affected, absenteeism numbers, or right, maybe there could be 100 other things. Maybe the corporate culture changed over the last year and people are really more invested in the company or something this year rather than last year. So we'd have to do more work to tie these two together. But we've at least shown that, there could be a relationship there. If from last year to this year, we didn't see the mean number of days off really change at all, if we had gotten our X bar new and it was like 6.2 or 6.4 or something, and I mean, we probably wouldn't really want to investigate any further whether we think that flex time had any effect. We'd probably say, okay, it doesn't really seem like it had an effect. If we do see an effect, we might have to do a little bit extra work to properly attribute that effect. But at least it suggests that there's something there to look into. Okay. So let's take this narrative idea, this idea that we have a certain worldview, we collect data, we compute a sample statistic, we look at that statistic in terms of from the perspective of the worldview that we have, and we ask if it's consistent. If it's inconsistent, then we might consider switching our worldview to something different that's more consistent with the data. So let's take this idea and let's make it a little bit more formal. Let me get my papers set up over here. Okay, so we're going to use an analogy of a jury trial to kind of take this a step closer to something very formal and very objective. We're not going to get quite there yet. We're going to make another pass, but we're going to try to get a little more objective, a little bit away from the more narrative approach and a little more towards something that we can tie the mathematics to. So what's the basic idea? We have a jury trial where the person is either innocent or guilty. We're going to presume that that the law is sufficiently well defined that if we were omniscient, if we knew everything there was to know about the actions that this individual took, that we could definitely say they're innocent or they're guilty. So we're going to assume that, if we knew everything, we could clearly put them into a bin, innocent or guilty. But obviously we don't know everything, right? So we have a test. We have a trial where we establish facts. And the result of that trial is going to be that the person is innocent or guilty. I'm going to just use innocent and guilty here as well. But realistically, we should say the trial determines actually guilty versus not guilty, right? So I'm going to kind of put this in quotations. We're determining through the test, through the trial, innocence versus guilt, but really the result would be guilty versus not guilty. And that's actually an important nuance, whether we would call the person innocent or whether we call them not guilty. It's an important nuance both in the trial, in the legal system, but also in how this analogy works with hypothesis testing. So let's consider a chart. There are two actual states. The person is guilty or they are innocent / not guilty. And there are two states for the test. Actually, I think I want to do this the other way. It doesn't matter which way you set this up, but so the test, the trial. It doesn't matter which way you set this up, but I'm trying to keep it consistent with some of the other tables that we've made in the past. And their actual status is either guilty or innocent / not guilty. So for right now, we're using innocent and not guilty as meaning the same thing, but we will discuss the nuance in a minute here. So the person has an actual status that hypothetically, if we knew everything there was to know about the situation, we could say clearly they're guilty or clearly they're innocent. The test, the trial, will claim that they are guilty or that they're innocent. We want the test, we want the trial to give results that are consistent with reality. That would be ideal. So if the trial says the person's guilty and they're actually guilty, that's a good result. And likewise, if the trial says they're innocent and they're actually innocent, that is also a good result. But we have two other quadrants where if the trial says they're guilty and they're actually innocent, that's an error. And if the trial says they're innocent, they're actually guilty, that's also an error. So this looks pretty similar to things like, for instance, our Bayesian setup for medical testing, or for things like confidence intervals, like how can we make an error? How can we make mistakes, right? When we're, say, setting up a confidence interval, we could set the interval, too high or too low or something like that and miss the mean or whatever it may be. So there are some analogies to some things we've talked about before. Okay, so we have some nomenclature here. So the first thing to note about our legal system is that a person is innocent until proven guilty. So that's something that I think we've all heard before, innocent until proven guilty, and that's an important tenet of our legal system. So the presumption of innocence, you're presumed innocent. So what does that mean? That means that the benefit of the doubt goes to innocence, and the job, in a sense, of the legal system, of the DA or of the jurors or kind of the trial, of the test, is to determine if there's enough evidence to overturn the presumption of innocence. So this is kind of the idea, the kind of, you know, abstract approach here is we go into the trial presuming that this is an innocent person randomly pulled off the street, improperly accused, or maybe not improperly accused, but unjustly accused or something like that. And then throughout the trial, there's a bunch of evidence, you know, that the person who robbed the bank is about this height, and the person in the courtroom is about this height, and they drove away in this car, and this person owns that same make and model and color of car, and right. So the evidence starts to stack up, and the point is that at some point there's going to be enough evidence. At some point, if the person is guilty and the trial uncovers enough evidence, there will be enough evidence where we say, okay, well, in light of all of this evidence, is it really sensible to hold on to my previous worldview that the person is innocent? Or should I say that the likelihood that they're innocent, in the face of all of this evidence, is so low that we're going to change our worldview and we're going to conclude that they're guilty? Does the evidence that was presented at the trial, is there enough of it to overcome that bar to switch the worldview from innocent to guilty? And that's kind of the job of the trial, to determine that. So now we maybe see why we might want to call this not guilty. Right? If we think in the extreme, in some kind of, you know, abstract extreme here, where we have evidence of innocence versus evidence of guilt, and we say, okay, to convict somebody, we have to be very far over here in the evidence of guilt side of things. If we fail to convict somebody of a crime, that doesn't mean that their defense attorney came out and made an incredible case that really convinced us beyond any doubt that the person's innocent. There could be a bunch of evidence that they're guilty, but just not quite enough to overcome that bar, because innocence gets the benefit of the doubt. So this is where our test declares guilty. You know, hypothetically, we might also have a region over here where we might say, oh, well, after this much evidence came out, the person is like almost definitely innocent, right? But importantly, there's a lot of space in the middle here where it's like maybe there's some evidence that they're guilty, but not conclusive. So the trial failing to provide enough evidence to overcome that high bar to prove guilt beyond a reasonable doubt, if they fail to meet that bar, that doesn't mean that it's been clearly and convincingly established that the person is innocent. It just means, well, you know, I mean, maybe it has been established that they're innocent very clearly, but maybe there's a decent bit of evidence they're guilty, but not quite enough for us to overturn that presumption of innocence. So that's why not guilty might be a better phrase to use here, both in the legal sense, but also we'll see in the hypothesis testing sense. The hypothesis testing setup has a very similar feel to it. So in hypothesis testing, maybe I'll switch colors here. So in hypothesis testing, this is going to be a general idea that isn't specific to the jury trial. We have kind of two competing worldviews. And we call these hypotheses. We have one hypothesis that we call H subscript 0. So H0 or H naught. This is H not like NAUGHT, not like NOT, like, you know, contradicting something. But H naught, H subscript 0 And we have another hypothesis that's H subscript 1, or sometimes written H subscript A. So that subscript is a lowercase a. I don't particularly like writing H subscript A because in my writing and in print, it actually looks a lot like a subscript 0, especially in the subscript when it's kind of small. A and 0 kind of look similar, but so I use H0 and H1. So H naught is what we call the null hypothesis. And it gets the benefit of the doubt. So there are lots of different setups for particular hypothesis tests for particular applications, but kind of speaking as in kind of generalities here, the null hypothesis would be kind of the kind of status quo, right? If I'm a researcher, if I want to prove that my drug works better than some standard of care treatment, H naught would be like the standard of care treatment is just as effective as my drug. It's kind of the status quo. Like I don't really have any reason to think that my drug would work better than what's out there already. Or another way of thinking about it, it's kind of the opposite of what I, as the researcher, want to be true or want to prove. I'm giving the benefit of the doubt to the other side of the argument. And then H1, the alternative hypothesis. This is essentially what I'm trying to prove. Again, speaking in generalities, there are different setups for different hypothesis tests, but so I kind of put that in quotes. That's not always a true statement. But that, you know, for the setups that we're going to use in the near future, that's pretty much going to be true. So if I was a researcher trying to show that my treatment works better than what's already out there, I would give the benefit of the doubt to what's already out there. I would say something like, okay, the null hypothesis, the thing that's going to get the benefit of the doubt is going to be that my treatment's no better than what's out there. The alternative hypothesis would be something like my treatment is better than what's out there. That's what I want to prove. That's what I'm trying to show with the stats. And then what I would do is I would collect a sample and I would try to use statistics from that sample to argue in favor of H1 and against H naught. I would try to argue that the statistics are such that to dig in your heels and still claim H naught in the face of such statistics would be nearly an absurdity, and that we should instead change our worldview to H1. So we typically write H naught and H1 inside of a curly brace like this. So if we were making, let's say, a claim about a mean or something like that, you know, maybe it's something like this. So this is what a certain, you know, setup of hypotheses might look like. Or to tie it, I guess we could tie it directly into our narrative by saying something like, that, right? If mu here was representing the current year's mean number of days off under the new flex time policy, the null, the kind of status quo is, well, it didn't change from 6.3. I think it was 6.3, right? 6.3 to 5.4. Yeah. So the null, the thing that gets the benefit of the doubt, the thing that's kind of the opposite of what the investigator is trying to prove, in a sense. The opposite argument is that the mean number of days off hasn't changed. So it just stayed at the status quo of 6.3, and that implementing the flex time didn't really do anything. What we're trying to provide evidence in favor of is that the mean has gone down, that flex time did reduce number of days off, and that the mean is less than 6.3. So how might we phrase the jury trial in terms of H0 and H1? Well, the thing that gets the benefit of the doubt, H naught, is innocent. And the thing that we have to surpass a high bar in order to argue in favor of, the thing that the evidence has to point strongly toward for us to change our worldview, the alternative hypothesis is the person is guilty. Right? So the result of the trial can be not guilty kind of under like two different regimes. It could be the person could be declared not guilty if there's really strong and convincing evidence that they're innocent, or they could be not guilty if it's kind of sufficiently muddy waters that we can't really tell the difference. Right? But to declare them guilty, it has to be very clear. The evidence has to be very clear that they're guilty. Okay. And there's one last little point that I want to make. There's this kind of saying that, related to what I just said, absence of evidence is not evidence of absence. So this is a quote that you might kind of hear from time to time, especially in the scientific world. And essentially what that means is that the absence of evidence that a person is innocent, if you can't find evidence that the person's innocent, that's not in and of itself evidence that they're guilty. So that's kind of what this is saying, right? In other words, you might be in the kind of muddy water area here where you're not really sure if they're innocent or guilty, so you probably ought not declare them guilty just because you've concluded or you failed to place them into this, left extreme. You ought not place them in the right extreme just because you failed to place them into the left extreme. Okay, so let's take a look at this idea now in a little more generality. So we have our hypothesis testing notation here. And we have two hypotheses. Let me erase this line out. I wanted that line above that green piece there. So we have our actual status that H naught is true or that H naught is false. And our test, our hypothesis test here, is we reject H naught in favor of H1. So I throw away H naught and go with H1 in light of the results of the test, or I fail to reject H naught, or I kind of just stick with H naught. I stay with the status quo. Note that I didn't say that I rejected H1 in favor of H naught. I haven't, failing to reject the null, which is the one that gets the benefit of the doubt. It's the default, it's the status quo. Failing to reject that, it just means that I didn't surpass the high bar required to switch to H1, the alternative. It just means I didn't pass that bar. So that's not to say that there's strong evidence in favor of H naught. It just means that we failed to reject H naught. We just failed to meet a high bar to overturn H naught. And so, as mentioned above, if we fail to reject H naught, if we, in some sense, accept H naught moving forward, if we stick with that hypothesis, and H naught is actually true, that is good. If we reject H naught in favor of H1 and H naught is actually false, that is also good. A perfect test would only have results in these two quadrants, but of course, no test is going to be perfect. We could fail to reject the null that's actually false, that we would ideally want to reject. Or we could reject a null when that null is actually true, when we would not want to reject it if things worked out perfectly. So we have two types of errors here. If we reject a true null, we call that a type 1 error. And if we fail to reject a truly false null, we call that a type 2 error. A type 1 error gets the the type 1 error rate gets the notation alpha. Or this is the probability that we reject H naught given H naught is true. Our type 2 error rate gets the notation beta. So the Greek letters alpha and beta, A and B, obviously where we get the word alphabet from, alpha, beta, first two letters of the Greek alphabet. This is the type 2 error rate. And it's the probability that we do not reject H naught given that H naught is false. Now, alpha and beta have an inverse relationship. So if all else is equal, so if we don't change the sample size or the standard deviation of the population or any of that kind of stuff, if we push one of these error rates down, that pops the other one up. Right? You might just ask, well, if we have these two different error rates, why not just make them both really, really small? And the answer is you can't do that. So if we push the type 1 error rate down, if we make choices about how we perform our hypothesis test to make alpha lower, then beta gets larger and vice versa. Right? It's a little bit like if you think of, say a screen for a disease, we know that if we're screening people for a disease, there are going to be some people who don't have the disease that we say do, and we send them for a follow-up. There are going to be some people who do have the disease that we say don't, and we miss those cases. The pickier we are, the more sensitive the assay is. So the pickier that we are, and the more easily that we say, yes, you have the disease for a certain test. Well, on one hand, we catch more people that actually have the disease, but on the other hand, we toss more people who don't have the disease into the group where we say, yes, you do have the disease. So if we're pickier, we can reduce what? The type 2 error rate at the expense of having a higher type 1 error rate. And vice versa. If we're less picky, if we need a whole lot of evidence to say the person has the disease, then just the opposite is true. So where we set this kind of sensitivity level of the assay or of our hypothesis test, that's where we're setting that trade-off between alpha and beta. Now, in practice, for hypothesis tests, we pick alpha. Often we pick it as 5%. And that, I guess that in a sense kind of implies what beta is, but we never really know what beta is. It's somewhat consistent in medical literature that beta is around 20% when alpha is around 5%. But I'll put like 3 question marks on that because, that's there are a lot of caveats that go with that. That's something that we might talk about in the cautions and pitfalls presentation. But practically speaking, we pick alpha to be a certain number. Quite often it's 5%. Sometimes it's 10% or 1%. In theory, it could be kind of any percentage you want, I guess. You could pick, 3.2% or something, but the numbers that people, typically use are 10, 5, or 1%. So we're controlling the type 1 error rate in our hypothesis test setup, and we're letting the type 2 error rate fluctuate to be whatever it ends up being for that type 1 error rate. Okay, I think that was all that I wanted to say on that point. Okay, so and here is just the kind of written out basically just typed up what I had just said and worked through. Yeah. So we have 3 tests we'll cover in chapter 8. 2 of them are tests for mu. So we have a certain worldview about mu, the null hypothesis, and another competing worldview about mu, the alternative hypothesis. And we want to test in light of some evidence, in light of some sample data, which hypothesis we want to use moving forward. And we'll use a z-test or a t-test, depending on the details of how things are set up and the information we know or don't know. And then the third thing that we'll see is, fairly similar to these other tests, is the z-test for proportion. And this obviously mirrors the confidence interval, the 3 different confidence intervals we had for mu and for proportion. We're not going to talk about testing for variance or standard deviation. Okay, there's one more thing that I do want to say, which I just realized I didn't say. And this is it's going to make a little bit more sense after we go through this these first couple of problems. But we want H0 and H1 to have 2 different characteristics. We want them to be mutually exclusive. In other words, I don't want there to be any possible scenario where H0 and H1 are true at the same time, right? I don't want my laws to be such that a person is simultaneously guilty and innocent of breaking the same law in light of the same action. Or if I'm making a statement about mu, like say this one up here, I don't want, my null hypothesis to be like mu is bigger than 5 and my alternative to be like mu is less than 6, where if mu was 5.5, both of them would be true at the same time. So I think that's pretty clear. If I have competing worldviews, that they shouldn't have any overlap. I don't want any situation where both worldviews are true at the same time, because if I end up in that overlap, then I don't really know which one to go with. The other one, which is a little more confusing, especially in light of how I just showed you that hypothesis test setup, is we want them to be exhaustive as well. In other words, every possibility is covered in either H0 or H1. So I want these two hypotheses, H1 and H1, to split up the space of possible realities perfectly into two pieces, no overlap and nothing, nothing missed out. So we also wouldn't want hypotheses like mu is bigger than 10 or mu is less than 5, because what if mu is 7, then which one do we go with? Now you might look at this and say, well, wait, my null is mu equals 6.3, my alternative is mu less than 6.3. What if mu was like 7 or 8 or 9? Well, this mu equals 6.3 is really kind of a shorthand in a sense for mu bigger than or equal to 6.3. We'll see why we kind of state the null the way that we do here in a little bit. But why is it doing that? There we go. But I have, I could kind of write the null this way, and that shows a little more of the exhaustivity. That in this case, my null hypothesis is that mu is bigger than or equal to 6.3. My alternative is that mu is strictly less than 6.3. And that perfectly splits the real line into two pieces. There's no overlap, they're mutually exclusive, and they're also exhaustive. Every potential mu is covered by exactly one of the two hypotheses. So this is an important theoretical point, a little less important for the practical calculations, but it's important to understand what's going on here, I think. Okay, so let's jump right into a z-test for mu. And we're going to kind of build up the idea of the hypothesis test from this problem. So we're not going to just go and just solve the problem, start to finish the way that we might after we kind of understand hypothesis testing a little better. We're going to maybe meander around a little bit as we get a feel for hypothesis testing. Again, it's not really the math or the calculations that are the hard thing in hypothesis testing. It's really the logic and understanding why we're doing this calculation or this mathematical operation at this place. Okay, so here we have, it's reported that national average credit card debt is $3,262. There's a college that believes their students have less credit card debt than the national average. They would like to say, publish this in their marketing material and make this claim. They think that might be a, something that people will find attractive about their college. But they don't want to make such a claim wantonly. They want to make sure that they have evidence in favor of that claim. So they take a sample. They take a sample of size 50. The X bar observed, the sample average for that particular sample that they observed is $29.95. So we could at just a very first glance say, well, $29.95 is less than $32.62. There seems to be some evidence that our that our students' mean credit card debt is less than the national average. Our point estimate is below $32.62. But of course, we know that there is variation, right? Well, suppose that we know that the standard deviation of credit card debt for our population of students is 1,100. And we know that there's going to be some standard error in X bar. So in essence, we can think of having an interval estimate surrounding $29.95, something like that. And the question is, well, I know that $29.95, that point estimate, has been subject to some sampling error, right? Maybe I just happen to sample a few more students who have low credit card debt than usual and a few fewer students who have high credit card debt than usual, and that kind of pushed my X bar observed down. But maybe that was just a strange sample, right? Maybe if I went out and took 10 more samples, every one of them would be, have an X bar observed above 32.62. So I would like to know, is $29.95, kind of just a little bit below 32.62 where it could have easily happened by chance? Or is it a lot below 32.62 where it was unlikely to have happened by chance? And to make clear the ideas of a little bit versus a lot, we're going to use the standard error. We're going to use the standard deviation of the population as well as the sample size. So what are our hypotheses? We would like to claim that our students' mean credit card debt is less than the national average. So let's let mu be our students' mean credit card debt. I would like to make a claim about mu that mu is less than 3262. This is what I'm going to try to provide evidence in favor of. So I want to put it as the alternative hypothesis. The other possibility is that mu is bigger than or equal to 3262. This is the worldview that, is not what I'm trying to prove. I'm going to give it the benefit of the doubt. So what am I really doing here? I'm saying that there's something that I want to be true. I'm going to give the benefit of the doubt to the other side of the argument. I'm going to give it the status quo. I'm going to give it the default status. Then I'm going to look at the data and I'm going to say, based on the data, can I overturn that null hypothesis in favor of the alternative, in favor of the thing that I want to show is true? So these are my hypotheses. So I have a little bit of a problem. If I consider the random variable x bar as the random variable, it's going to be normal, right? N bigger than or equal to 30. So we can use central limit theorem here. The mean is going to be mu, and the standard deviation is going to be something. And I really want to use my central limit theorem to figure out what these, say, probabilities of certain types of errors and so on are. My problem, though, is that, well, the thing that's the mean of my distribution here is precisely the thing that I don't know about, right? It's precisely the thing that I'm trying to figure out. So this is a fundamental problem. We had kind of one approach to this in confidence intervals. We're going to take a different approach here. Remember that H naught gets the default, the status quo. It gets the benefit of the doubt. In other words, we kind of like assume that H naught is true, and then we evaluate how strange the data would be, how strange it would be to get such data if H naught was actually true. Let's go back up here just to remind ourselves of that, right? We said you have a hard choice to make. You can dig in your heels and say that the mean number of days off has not changed. But for that to be true and for us to have gathered this data, it would take like a minor miracle. It would be a 1 in 1,000 event, quite a rare event to get such data if that was actually true, that the mean number of days off is not decreased. And the other thing you can do is you could change your worldview. You could say, okay, I think that the mean number of days has actually decreased. Right. So if it's extremely unlikely for us to get such data under the null hypothesis, that's whenever we would want to, and importantly, if it's more likely to get such data under the alternative, that's whenever we would want to reject the null in favor of the alternative. So H naught gets the benefit of the doubt. So all of our hypothesis testing calculations start with the same statement. And that statement is assume H naught is true. When we're actually going to dig into calculations, we always start with this statement. And I always write it down. I suggest you write it down too, just so that it's clear what an assumption, what assumption you're making for the following calculations. We assume the null is true. Well, now X bar is normal, and we know something about the mean. We know that the mean is something like it would be under H naught. So that means that the random variable X bar is centered at some mean we'll call mu naught, some kind of null hypothesized mean. We're going to clear this up in a minute because, well, there's a heck of a lot of means that are bigger than or equal to 3262, but we're going to deal with that detail in just a minute here. But if we assume that that H naught is true and that X bar is centered at some null hypothesized mean, in other words, we now know that X bar is not centered at a mean that's less than 3262. Well, I want to provide evidence. My overall goal is to provide evidence that mu is less than 3262. So X bar observed low does provide evidence. High does not, right? If I got an X bar observed, if I sampled my 50 students and none of them had any credit card debt at all, if X bar observed was like 0 for every one of my students that I sampled, I'd be very confident in making this claim, right? If, say, X bar observed was like 0. If X bar observed was, say, 4,000, I wouldn't even need to do anything else. I wouldn't need to look any further. I know that the claim is not true. Okay, so coming back up here, remember the type 1 error is the thing that we're going to control. That's the probability that we reject H naught, given that it's true. So assuming H naught is true, so this distribution is given H naught true, given H naught is true, I would reject H naught for X bar observed far to the left, but not far to the right. So there's some cutoff here, or for a given X bar observed. If I reject H naught for this X bar observed, let's say at 3,000, I'd also reject for 2,900 or 2,800 or 2,700, right? Because that would just be more evidence in the correct direction. It would be further in the direction of providing good evidence against H naught in favor of H1. So this is where I'd reject H naught. But in that case, I would reject a true null. This would be the type 1 error rate. So if I were to reject for this particular X bar observed in this particular sample, then that would suggest a certain type 1 error rate, and that's what I want to bound. So here I would compute my type 1 error rate for a specific X bar observed, and I'd say if this error rate is less than some maximal allowable error rate. Maximum allowable error rate, which we typically set as 1%, 5%, or 10%. This would be something we would have to decide in advance. We have to decide really before we even ran the experiment or got the data what our maximum allowable error rate is. This is a choice that a person has to make. Kind of a pretty standard one is just to use 5%, but you could use different ones if that's common in a certain field or something like that. But if this type 1 error rate that we would compute here is less than the maximum allowable error rate, then rejecting H0 on the basis of this sample wouldn't cause a type 1 error rate that's, that's unacceptably large. So then we would reject H0 in favor of H1. Okay, so we have a little bit of notation for this. Again, the complexity here is the notation, the logic, why we're doing all of this. It's less in the actual calculation of all this, which is why I'm trying to avoid writing down any numbers at this point. So I'm trying to avoid that because I want to talk through the logic before we get to that point. And then we'll, I think, see more clearly where all these numbers come from. So this type 1 error rate, in other words, the chance that we make a type 1 error if we were to reject H0 in favor of H1 on the basis of this sample, we call this the p-value, or often we just call it p. And this p-value, we ask, is it less than alpha, which is the maximum allowable type 1 error rate? So this is the big question. If we were to reject H0 in light of this particular evidence we got, sometimes we would make an error. Sometimes H0 would be true, and we'd reject it anyway. We don't want to do that too often. So we figure out how often that would happen. That's the p-value. And we compare that to alpha, the pre-chosen maximum allowable type 1 error rate. So for this problem, alpha would be 5%. In a different problem, it could be 10%, it could be 1%, it could be 7.5%. But people typically use 5% or a little less often, 1 or 10%. So this is the big question. Remember that alpha, this is the same alpha as up here. It's the type 1 error rate for the test in general. And it's the thing that we pick. We set alpha to be some number. And we unfortunately kind of never really know what beta is. We set alpha, and then beta kind of, is left to kind of float to make up the difference in a manner of speaking. Right, so the decision criterion is find the p-value, and if p less than alpha, reject H0. If p greater than or equal to alpha, do not reject H0. So that's the decision criterion. Okay, so again, what's the idea? Just to quickly recap what we just said. We have a null and alternative hypothesis. Our alternative hypothesis has a less than sign, mu less than some number. So X bar observeds that are low are going to be evidence against H0 and in favor of H1. X bar, the random variable, is normal, but its mean is kind of unknown because it's the same thing that the null hypotheses are talking about. But if I assume H naught is true, then I've at least kind of cordoned the mean off to being bigger than or equal to 3262. Let's suppose that I pick a mean in that range, maybe 3300 or something, call that mu naught. If H naught is true for that particular mu naught, I see that X bar observed is 2995 here. But if it were 2990 or 2900 or 2800, that would be even stronger evidence against H naught in favor of H1. So I would, if I reject for this X bar observed, 2995, I'd also reject for all those other X bar observed to the left had I gotten those. So this area to the left of X bar observed, this is when we would reject the null, even though it's true. This is when we would make a type 1 error. The type 1 error rate is this area in this normal distribution to the left of X bar observed. And that type 1 error rate we call the p-value. Typically, we just write p for it. And we compare that to the preset, predefined maximum allowable type 1 error rate, alpha. In this particular problem, that would be 5%. And then our decision criterion is if p is less than alpha, in other words, if the error rate that we would actually achieve is less than the maximum allowable error rate, then we reject H naught. Or if the error rate that we would actually see if we rejected under this sample is bigger than or equal to the maximum allowable error rate, that's too much error for us to accept. We're not going to reject H naught in that case. Okay, we have one detail to iron out. How the heck do I choose mu naught? Well, I could choose mu naught kind of in a sense anywhere to the right of 3262 and test against this, right? Maybe I choose mu naught is, say, 3300, or well, heck, why not just choose mu naught to be like 10 million, right? If I choose mu naught to be some huge number, then this tail is always going to be super small, right? Because X bar observed is like what, 2995. So if I just choose mu naught to be like way, way far in this interval, over to the right in this interval, then that makes that tail tiny and I can always reject. Why wouldn't I do that? Well, because if H naught is true, I don't know what H naught is. I just know that it's bigger than or equal to 3262. I see that the larger that I pick mu naught to be, the larger the mu naught that I choose to test against. In this case, the larger that mu naught is, the further away it's going to be from X bar observed, and the smaller the tail is going to be. So, I mean, I know that I could reject for a mu naught of 10 million, basically, no matter what happens with this sample. Like the students, nobody's going to have $10 million of credit card debt, as well, nobody in general, I think, is going to have that much, but definitely not as a college student. Well, so I note that I can easily reject for mu naughts that are way far to the right. What's the hardest mu naught for me to reject against? If I was going to pick a mean in this interval to test against, where I could say, if I can reject for this mu naught, then I can reject for all of the others bigger than it as well, or all of the others in this interval. Well, I would choose the one right on the border. 3262 is the closest mu naught in this interval from 3262 to infinity. It's the closest one to X bar observed. So I'm always going to test against the mu naught that is right at the boundary. So if H naught is true, then mu naught is in close 3262 to infinity, if I can reject against a mu naught of 3262, I could also reject against the mu naught of 3263, right? That's going to give more separation here between mu naught and x bar observed. That's going to make that tail smaller, the p-value smaller. It'll still be less than alpha. If I chose mu naught to be 3300, that's going to give even more separation here. That's going to make that tail much smaller, that area much smaller. It's still going to be less than alpha. I can still reject. So if I can reject for mu naught of 3262, can reject for any other mu naught bigger than 3262. So mu naught equals 3262 is the most conservative one to test against. It's the one that gives the most benefit of the doubt to H naught. So I've kind of drawn all over this. Let me erase this just to clean it up a little bit. So I had mu greater than or equal to 3262 here, but in practice, we usually don't write that for mu naught. In practice, usually we would just write mu equals 3262 because of this idea. But it's important to realize that, if we fail to reject H1, we're not like arguing that we think that mu is exactly 3262. And we're kind of arguing that, we've just failed to surpass this high bar that mu less than 3262. And we kind of instead adopt the worldview of either mu equals 3262 or mu bigger than or equal to 3262. Okay, so we now can put a 3262 here. And at this point, believe it or not, we have enough information to do all the computations we need. So I'm going to clean this up just a little bit here. So this was kind of scratch work to just get the idea straight. And I'm just going to rewrite a couple of the pieces. So here, we're still under assume H naught's true. Then X bar is normal with a mean of 3262, right? That borderline mu naught, if we can reject against a mu naught of 3262, we can reject against any other mu naught in that interval to the right. We have an X bar observed, 2995. If we were to reject for X bar observed of 2995, we'd also reject for any X bar observed to the left of that, 2990, 2900. These would all be stronger evidence against H naught in favor of H1. This area is the p-value. Oh, and X bar is normal with a mean of 3262 and a standard deviation. Well, that's the standard error, right? That's sigma over root n. 1100 over root 50. And so what do I have? I want to compute the p-value, which is the probability that X bar, the random variable, is less than 2995. Why is this symbol less than and not greater than or something? Well, it's because it ultimately comes back to this symbol being less than. So that's our p-value. This is the probability that, well, what's the z-score for this? 2995 minus the mean over the standard deviation. And let me switch my share now. Switch my share to full screen. So here my numerator is 2990. Oh, 2995 minus 3262. That's going to be divided by 1100. And then this over root 50 is in the bottom, so it's going to come up to the top as a times root 50. If you don't like that, you can use parentheses in the denominator and keep it divided by down there, but that's negative 1.72. So what's the probability z less than negative 1.72? Here's negative 1.7012. That is 4.27%. So what do I see? I see that P, the P value, probability of a type 1 error, if we reject H naught, is 4.27%. This is indeed less than 5%, which is alpha, which is our maximum allowable error rate given in the problem. You have to be given that, right? That's not something that comes out of the math. That's something that somebody says in our industry or our field or whatever. We use alpha equals 5%, something like that. So I can say now, since P less than alpha, we reject H naught in favor of H1, and we can make the claim. So we are on solid statistical footing here to make this claim that our credit card or our college students have credit card debt less than the national average. And if somebody were to challenge that, if they were to come to us and say, hey, you made this claim, what's your support for that? I could give them this sample along with this argument, and that would be my argument in favor of the claim that I'm making. So you see that the calculations, these are the same calculations we've done, in chapter 6, or kind of similar calculations we'll see from a slightly different perspective that we've done in chapter 7. The calculations aren't anything new. We're just computing a probability of a normal distribution. But the question is, where does all of this stuff come from, right? Why do we set up the hypotheses this way? Why do we assume H naught is true? Why do we pick this as our mu naught to test against? Why do we care about the p-value? Why do we care about this area to the left of x bar observed on this distribution x bar? That's the difficulty of hypothesis testing. And it's not easy, right? The logic is very backwards. Essentially, we're arguing by contradiction. We're saying if we assume the opposite of what we think is true, gather evidence, is how unlikely would it be to get such evidence if the thing that's the opposite of what we think is true was actually true? If it's quite unlikely, then, and if it's more likely to happen under our worldview, then we switch to our worldview. So it's a very backwards type of argumentation. Why do we do it this way? Well, the practical reason that we do it this way is it lets us make this huge statement here. Assume H naught is true, which lets us do this, which gives us enough meat, so to speak, that we can actually run a computation. If I wasn't able to do that, if I didn't argue with this kind of backwards type of argument, if I said, I think mu is less than 3262, like, what do I think mu is on the basis of this sample or something like that? The result would be something more along the lines of Bayesian statistics. It'll be more along the lines of something like, I start with a null versus an alternative hypothesis. I start with some distribution over those hypotheses. I have some evidence, some sample data, and I update that distribution in light of that evidence. And then on the result of that distribution, I make an argument one way or the other for one of the hypotheses. But as we mentioned before, that process can require a lot of computational resources. That's not something that was popular, say 100 or even 50 years ago. So there are different reasons for taking this approach. But the big thing that we get out of this kind of backwards approach, this argument by contradiction, is we get this combined with this, which gives us enough material to perform a computation and get a number out. And the logic does hold. It's just that it's hard to interpret, right? It's like when you say, what does a p-value mean? When I tell you the p-value is 4.27%, that does not mean the probability the null is true is 4.27%. That would be like a Bayesian statement. What this means is that if the null were true, and if mu naught were right at that border, 3262, then the probability of us seeing a sample with an x-bar observed this extreme or more extreme in this left-hand direction would be 4.27%. Right. That's a very complicated explanation of what a p-value is. And that's one of the downsides of hypothesis testing. That's also probably the main thing that makes hypothesis testing difficult, is the interpretation of what these results mean. So another thing that we might say, I can't get my thing to select here for some reason. There we go. Trying to get myself a little more room here, but another thing we might say is that there is statistically significant evidence that mu is less than 3262, or statistically significant evidence in favor of H1 or something like that. Or something like this sample represents statistically significant evidence that mu is less than 3262, right? There's a bunch of different ways to kind of phrase these results. But at the end of the day, we have provided some statistical evidence in favor of the alternative hypothesis and against the null hypothesis. And that's the important takeaway. We haven't proven that H1 is certainly true. This could have happened by sampling error. It could be, a rare event that only happens a little over 4% of the time. But we set a cutoff and we said, if we would make a type 1 error less than 5% of the time, then we'll reject. And we've met that cutoff, right? We set a bar. It's kind of a high bar. We have to make errors less than 5% of the time, or this type of error less than 5% of the time. We have to be correct in this sense more than 95% of the time. And we have, in this case, surpassed that high bar. So we can reject H0 in favor of H1. Okay, when we come back, we'll look at a couple more examples. The next couple examples will actually go pretty quickly. So even though we didn't quite get through all of the tests for the mean, we didn't get to a t-test for the mean. We'll do a couple examples when we come back, but the problems themselves will actually go pretty quickly now that we hopefully kind of have a grasp of how the machinery, so to speak, for hypothesis testing works. That's really the hard thing to understand. I would recommend before next class read through the kind of introduction hypothesis test sections in the book. So understand what the errors are, understand the structure of the hypothesis test, the logic. Maybe read back through this narrative here, just now that we have a little more exposure to it, read back through the narrative and see if you can get a deeper understanding of what the narrative was saying and how that all ties in, and think back to this jury trial. So maybe kind of review some of this material in preparation for Wednesday's class, when we'll just continue on with these next couple of examples. We'll see a couple of different calculation-based approaches to answering the same question. And and then we'll move on to test for proportions. So that's next time. I will see you all then.